Hello everyone, this video is for visually impaired students. Let's start chapter organometallic compounds. Introduction. Organic compounds in which a metal atom is linked directly to a carbon atom are called organometallic compounds. A large number of metals, example lithium, sodium, magnesium, zinc, mercury, lead, cadmium, etc., form such compounds. The organic part is generally an alkyl, alkynyl, or an aryl group. They are named simply by adding the name of the metal to the name of the organic group linked to the metal. For example, methyl lithium, ethyl magnesium, dimethyl cadmium, diethyl zinc. The carbon metal bond in organometallic compounds differs widely, varying from bonds which are essentially ionic to those which are largely covalent. For example, thus, the extent of the ionic or polar character of the bond is largely determined by the electropositive nature of the metal. More electropositive the metal, more is the ionic character of the carbon metal bond. In general, the ionic character of the carbon metal bond follows the sequence CK, then CNA, then CLI, then CMG, CAL, CZN, CCD, and CHG. The reactivity of organometallic compounds also depend upon the nature of the carbon metal bond. Generally, the larger the ionic character of carbon metal bond, the more reactive is the organometallic compound. However, compounds having intermediate ionic character are of greater importance because of their lower reactivity and selective nature of their reactions. Organometallic compounds are extremely useful for the synthesis of a vast variety of organic compounds. Apart from these, many of the organometallic compounds are commercially important as well. For example, tetraethyllead is extensively employed as an anti-knock compound. Organotin compounds are used as antioxidants in rubber products. Phenyl mercuric acetate is used as fungicide and disinfectant, and organoarsenic compounds are used in medicine. Organomagnesium compounds, Grignard reagent. Organomagnesium halides are extremely important reagents in synthetic organic chemistry. The reagents are commonly known as Grignard reagents after the name of the discoverer. Victor Grignard received the Nobel Prize in Chemistry in 1912 for the discovery. The general formula of Grignard reagents in RMGX or ARMGX, where R represents an alkyl group and AR represents an aryl group. Preparation. Grignard reagents are prepared in laboratory by the action of an alkyl or an aryl halide, preferably bromide or iodide or magnesium metal, in dry ether. Rx plus Mg in presence of dry ether gives RMgX. Besides ether, tetrahydrofuran THF, dioxane, dimethyl oxythane or dimethyl ether of diethylene glycol, tertiary amines, etc. can also be used as solvents. In fact, THF is considered to be the solvent since it increases the reactivity of an alkyl or aryl halide towards magnesium. It is because of the reason that the Grignard reagents of less reactive aryl and vinyl halides, which are difficult to prepare ether, are prepared in THF. Bromobenzene plus Mg in presence of dry ether gives phenyl magnesium bromide. Chlorobenzene plus Mg in presence of THF gives phenyl magnesium chloride. Vinyl chloride plus Mg in presence of THF and on heating gives vinyl magnesium chloride. Further, it has been found that for a given alkyl group, the ease of formation of Grignard reagent is of the order iodide is greater than bromide is greater than chloride. The alkyl or aryl magnesium fluorides are however unknown. For a given halogen atom, the order of reactivity is CH3X, then C2H5X, then C3H7X, etc. That is, the formation of Grignard reagent becomes increasingly difficult with increase in the number of carbon atoms in the alkyl group. The use of alkyl halides is avoided since they readily lose a molecule of hydrogen iodide to form an alkene. Tertiary alkyl chlorides may then be used. Procedure for the preparation of Grignard reagents. Alkyl or aryl halide is added slowly to a perfect clean and dry flask containing dry magnesium turnings covered by a layer of absolutely dry ether or THF. The reaction mixture is warmed a little when an exothermic reaction should start soon. If the reaction does not start within 5 minutes, a few crystals of iodide are added and the reaction mixture is warmed a little. A vigorous reaction soon sets in and magnesium gradually dissolves, forming a cloudy solution of the Grignard reagent. Precautions in the preparation of Grignard reagent. During the preparation of Grignard reagent, the following precautions must be observed. Number 1. The apparatus should be perfectly dry and protected from moisture by using a CaCl2 guard tube. Number 2. All the reagents and solvents, that is alkyl or aryl halide, magnesium, metal and ether, must be absolutely dry. 3. Ether used as solvent must be completely free from alcohol. This can be done by first washing ether several times with water, followed by drying over anhydrous CaCl2 for 1 to 2 days and subsequent distillation over sodium. 4. An atmosphere of dry nitrogen should be maintained throughout the course of the reaction. These precautions are necessary since Grignard reagents are decomposed by moisture and react with oxygen and carbon dioxide to form alcohols and carboxylic acids respectively. The ethereal solution of Grignard reagent thus obtained is generally used as such for various reactions by adding to it the other reagent. Mechanism. The mechanism of the formation of Grignard reagent is still not certain. According to Gomberg and Beckmann, the reaction commences with the formation of a small amount of magnesium halide and then proceeds by a free radical mechanism. Rx plus Mg plus Xr gives Rr plus Mgx2. Mgx2 plus Mg gives 2 Mgx. Rx plus Mgx gives R radical plus Mgx2. R radical plus Mgx gives R Mgx. This mechanism also elegantly explains the initiating effect of iodine, which may be ascribed to the formation of magnesium iodide from magnesium iodine. Structure of Grignard reagent. The structure of Grignard reagent has not been finally settled so far. The recent research has shown that the actual structure varies with the particular Grignard reagent and the solvent used for its preparation. Grignard and Blaise observed that evaporation of ethereal solutions of Grignard reagent resulted in a white solid having the composition RMgX 2C2H520. They suggested that ether molecules were present as ether of crystallization. X-ray analysis of these dietherates suggests that 4 groups are arranged tetrahedrally as shown in Formula 1. The Formula 1 suggests that ether does not merely provide a medium for the reaction, but it also helps to resolve the Grignard reagent formed due to solvation by ether molecules. This is supported by the observation that Grignard reagents can be prepared even in benzene solution in presence of a tertiary amine, which coordinate with magnesium like ether and thus dissolves it. Further, Formula 1 shows the Grignard reagent in the monomeric form, but physical studies has revealed that Grignard reagent exists as 1:1 complex of a dialkyl or diaryl magnesium and magnesium halide coordinated with molecules of ether. These two species are held together by halogen bridges as shown in Formula 2. However, for the sake of convenience, the formula RMgX has been used to represent alkyl magnesium halides in the text. Reactions of Grignard reagents. The carbon-magnesium bond in Grignard reagent is highly polar due to large electronegativity difference between carbon and magnesium. Consequently, due to greater electron density around carbon, the alkyl group in Grignard reagent can act as a carbanion or a nucleophile, that is, it can attack any electron deficient center in other molecules. In other words, Grignard reagents chiefly undergo nucleophilic substitution or nucleophilic addition reactions. 1. Nucleophilic substitution reactions. Grignard reagents reacts with compounds containing an hydrogen or halogen atom. All such reactions involves the nucleophilic attack of the alkyl group of the Grignard reagent on the electron deficient center as shown below. 2. Nucleophilic addition reactions. Grignard reagent react with compounds having a multiple bonds such as carbonyl group, etc. to form addition products which when hydrolyzed yield a variety of compounds. In all such reactions, the addition of the nucleophilic group of RMgX, that is OR negative, occurs at the more electropositive end, and that of MgX group at more electronegative atom of the multiple bond. Synthetic uses of Grignard reagent. Grignard reagents serve as extremely valuable starting material for the synthesis of a vast variety of organic compounds. They have attained a position in synthetic organic chemistry unrivaled by any other class of the compound. To illustrate this, some important synthetic applications of Grignard reagents are described below. Alkanes. A. By action with active hydrogen containing compounds. Active hydrogen containing compounds such as water, alcohol, thioalcohol, carboxylic acid, hydrogen sulfide, ammonia, amines, terminal alkynes, etc. react with Grignard reagent to form an alkane corresponding to the alkyl or the aryl group of the Grignard reagent. RMgX plus HB gives RH plus MgBX, where B is OH, OR, SR, OC, OR, NH2, NHR, NR2, etc. Since methane is evolved quantitatively when CS3MgI is treated with compounds containing active hydrogens, therefore these reactions can be used for estimation of OH, NH2SH groups in organic compounds. The method employed is called Zervitinov's method. Aryl magnesium halides also behaves in a similar manner. Example, phenyl magnesium bromide plus H2O gives benzene plus MgOH B. By action with reactive alkyl halides, Grignard reagents react with reactive alkyl halides such as T-butyl chloride, benzyl chloride, etc. to form alkanes. 3. Alkanes. Grignard reagents, being weak nucleophiles, do not react with simple alkyl halides. However, compounds containing more reactive halogens such as allyl iodide, etc. react with them, giving alkene examples. Allyl iodide plus CS3MgI gives 1-butene plus MgI2. 3. Alkynes. Grignard reagents react with terminal alkynes forming alkynyl Grignard reagents. Upon treatment with alkyl halide give higher alkynes. For example, CS3C triple bond CH, that is propyne plus CS3MgI gives propenyl magnesium iodide plus CH4. Primary alcohols. A. By action with ethylene oxide followed by hydrolysis, Grignard reagents with ethylene oxide to form addition products which on hydrolysis with dilute hydrochloric acid form primary alcohols containing 2 carbon atoms more than alkyl halide. Ethylene oxide plus Grignard reagent give addition product on hydrolysis gives 1 degree alcohol plus MgOHX. B. By action with formaldehyde followed by acid hydrolysis, when treated with formaldehyde, Grignard reagent forms an adduct which on hydrolysis with dilute hydrochloric acid gives a primary alcohol. Formaldehyde plus Grignard reagent gives addition product which on hydrolysis gives 1 degree alcohol plus MgOHX. C. By action with oxygen, primary alcohols are formed by passing dry oxygen through the solution of a Grignard reagent followed by acid hydrolysis of the resulting addition product. Example, N-propyl magnesium bromide on reaction with half oxygen gives CS3CH2 CH2O MgBr, which on hydrolysis gives N-propyl alcohol plus MgOHBr. 5. Secondary alcohol. A. By action with aldehydes other than formaldehyde followed by acid hydrolysis, acetaldehyde on reaction with CS3MgI gives CCS3 twice OHMgI, which on reaction with hydrolysis gives isopropyl alcohol. B. By treating an excess of a Grignard reagent with ethyl formate, the reaction takes place in 2 steps. Grignard reagent first reacts with ethyl formate to form an aldehyde, which in turn reacts with another molecule of Grignard reagent to yield an adduct which forms a secondary alcohol on hydrolysis. Ethyl formate on reaction with Grignard reagent gives an additional product which is unstable, and after this it gives aldehyde. 6. Tertiary alcohols. 1. By reaction with ketones followed by hydrolysis. Ketones on reaction with RMGX gives a product which on hydrolysis gives 3-degree alcohol. Number 2. A tertiary alcohol having at least two similar alkyl groups may be prepared by the interactions between an ester other than formic ester and an excess of Grignard reagent. The reaction proceeds in two steps. Ester plus Grignard reagent gives additional products which after gives ketones, and each on reaction with RMGX gives another additional products which on hydrolysis gives 3rd-degree alcohol plus MgOHX. 3. By reaction with acid chlorides and anhydrides, Grignard reagent react with acid chlorides or anhydrides to give additional products which upon acid hydrolysis give tertiary alcohols. The reaction takes place in two stages. For example, acetyl chloride on reaction with CH3MgBr gives an additional product which gives acetone, and after this again with hydrolysis it gives tert butyl alcohol. 7. Ethers. Grignard reagent react with lower halogenated ethers to yield higher ethers. Monochloromethyl ether plus CH3MgI gives ethyl methyl ether plus MgICl. 8. Aldehydes. When a Grignard reagent is treated with ethyl formate, an aldehyde is formed. However, with excess of Grignard reagent, the product obtained is secondary alcohol. B. Aldehydes are obtained in a better yield if ethyl orthoformate is employed instead of ethyl formate. This is so since the formation of acetal in this case prevents the formation of secondary alcohol. Ethyl formate gives acetal which on hydrolysis gives aldehyde plus 2C2H5OH. See, aldehydes may also be obtained by the interaction between a Grignard reagent and hydrogen cyanide followed by hydrolysis of the adduct formed. Hydrogen cyanide plus Grignard reagent gives additional products which on hydrolysis gives aldehyde plus NH3 plus MgOHX. 9. Ketones. By treatment with alkyl cyanides followed by acid hydrolysis, for example acetonitrile plus CH3CH2MgBr gives CH3C, CH2CH3 and MgBr, which on hydrolysis gives ethyl methyl ketone or 2-butanone plus NH3 plus MgOHBr. B. By action with acid chlorides. As discussed, equimolar amounts of Grignard reagent and an acid chloride give an additional product which forms ketones on hydrolysis. If Grignard reagent is used in excess, tertiary alcohols are obtained as ultimate products of the reaction. Acid chlorides gives ketone and then on hydrolysis it gives 3rd-degree alcohol. 10. Monocarboxylic acids. Grignard reagent interact with dry ice to form additional products which on acid hydrolysis gives monocarboxylic acids. Grignard reagent plus carbon dioxide gives an additional product which on hydrolysis gives monocarboxylic acids plus MgOHX. Esters. By action with ethyl chloroformate, equimolar amounts of Grignard reagent and ethyl chloroformate react together to form higher esters. Ethyl chloroformate plus Grignard reagent gives additional product which is unstable, which on hydrolysis gives higher esters plus MgXCl. 12. Thioalcohols. Grignard reagent react with sulfur to give an additional product which gives a thioalcohol on hydrolysis. RMGX plus S gives an additional product which on hydrolysis gives thioalcohol plus MgOHX. Phenols. Aryl magnesium halides react with oxygen to form additional products which upon hydrolysis gives phenol. Phenyl magbromide plus half oxygen in presence of dry ether gives phenyl oxy magnesium bromide which on hydrolysis gives phenol. Alkyl cyanides. By interaction of Grignard reagent and cyanogen chloride or cyanogen, C2H5MgBr plus CnCl gives ethyl cyanide plus MgBrCl. Excess of Grignard reagent is avoided since it will react further with alkyl cyanide to yield ketones. Primary amines. Grignard react with chloroamine to form primary amines. RMGX plus NH2Cl gives RNH2 plus MgXCl. Reasonable aids of primary amines is obtained only with Grignard reagents containing tert alkyl groups. Primary amines can also be prepared in satisfactory yields by the action of Grignard reagent on orthomethyl hydroxylamine. 2-RMgCl plus CH3ONH2 gives addition product which on hydrolysis gives 1-degree amine plus MgOHCl. Sulfonic acids. On passing sulfur dioxide into a well-cooled solution of Grignard reagent, an addition product is obtained which on hydrolysis gives sulfonic acid. Sulfur dioxide plus Grignard reagent gives a product which on hydrolysis gives sulfonic acid plus MgOHX. Diothioic acids. These are produced by the action of Grignard reagent with carbon disulfide followed by acid hydrolysis. Carbon disulfide plus Grignard reagent gives an addition product which on hydrolysis gives dithionic acid plus MgOHX. Organometallic compounds. Grignard reagent with inorganic halides interact with each other resulting in the formation of other organometallic compounds. 2. C2H5 MgBr plus HgCl2 gives diethyl mercury plus 2 MgBrCl. Abnormal addition of Grignard reagents. Number 1. Addition of hindered ketones. If the Grignard reagent or the ketone contains branching at the alpha carbon, sometimes the usual addition reaction does not occur due to steric hindrance. Instead, reduction occurs in which a hydride ion is transferred from the Grignard reagent to the ketone via a six-membered cyclic transition state in a manner similar to Mirvin-Pondorov-Verley reaction. For example, when isopropyl magnesium bromide is added to diisopropyl ketone, the expected third-degree alcohol is not formed. Instead, the secondary alcohol diisopropyl carbinol is obtained by reduction of the keto group. Number 2. Addition to alpha-beta unsaturated compounds. Alpha-beta unsaturated carbonyl compounds react with Grignard reagents to give 1,2 and 1,4 addition products. The orientation of addition is often controlled by steric factors. In general, substitution at the carbonyl group favors 1,4 addition while substitution at the double bond favors 1,2 addition. For example, 1,2,3 triphenyl prop 2 in 1 on gives 1,2,3,3 tetraphenyl propane 1 on hydrolysis and in presence of pH MgBr. In most cases, both products are formed, but alpha-beta unsaturated aldehydes nearly always give exclusive 1,2 addition products when treated with Grignard reagent. However, the extent of 1,4 addition of Grignard reagents can be increased by carrying out the reaction in presence of cuprous chloride or cupric acetates, etc. This is called conjugate addition and probably occurs by a free radical mechanism. Limitations of Grignard synthesis. Grignard reagents suffer from the following limitations. Grignard reagents are sensitive to moisture, oxygen, and carbon dioxide and hence must be protected from them. This makes the handling of Grignard reagents difficult too. Grignard reagents cannot be prepared from alkyl halides containing other reactive functional groups such as OH, SH, NH2, COOH, SO2, CHO, carbonyl group COOR, CN, etc. since they all react with them. One only alkyl halides containing a few other groups such as ROR, AR, X, etc. can be used to form Grignard reagents. 3. Generally, branching of the carbon chain near the functional group prevents reaction probably due to steric hindrance. For example, CH3-MgBr or CH3-MgI does not react with ditert-butyl ketone. Similarly, if the Grignard reagent contains large alkyl groups, the reaction is sometimes prevented again due to steric hindrance. For example, isopropyl methyl ketone reacts with CH3-MgI but not with tert-butyl magnesium chloride. 4. Compounds which are capable of enolization liberate hydrogen with Grignard reagent. For example, ethyl acetoacetate enol form and then with CH3MgI it gives CH3CCH2COOC2H5 plus CH4. 5. Nitro compounds cannot be used in Grignard synthesis since they oxidize the Grignard reagents. Despite the above limitations, Grignard reagents are still the most important tools in organic synthesis. Organozinc compounds. Although organozinc compounds of the type R2Zn are not commonly used in organic synthesis, they are particularly useful when milder reagents are required. Method of formation. Following methods have been used for the preparation of organozinc compounds. 1. From alkyl halides. Alkyl iodide react with zinc copper couple in high boiling point ether to form alkyl zinc iodides, which upon subsequent distillation in an atmosphere of CO2 undergo disproportionation to give dialkyl zinc compounds. 2Ri plus 2Zn gives 2RZnI, which on distillation gives dialkyl zinc plus Zni2. 2. From organoaluminium compounds, treatment of trialkyl aluminium with zinc chloride gives trialkyl zinc compounds. ZnCl2 plus triethyl aluminium gives diethyl zinc 2C2H5 2AlCl. Physical properties: dialkyl zinc compounds have linear geometry due to sp hybridization of zinc atom. They are non-polar, low boiling liquids or low melting solids soluble in organic solvents. The lower zinc compounds are highly inflammable in air and hence are usually prepared and used under CO2 atmosphere. Chemical reactions: the chemical reactions of organo-zinc compounds are similar to those of the Grignard reagents, with the only difference that they are less reactive. For example, they do not react with CO2 and react only slowly with cyanides, ketones, and esters. Some important chemical reactions of dialkyl zinc compounds are discussed below. 1. Reaction with water. They readily react with water, forming alkanes. Reaction with alkyl halides. Dialkyl zinc compounds do not react with 1 degree and 2 degree alkyl halides. They react only with 3 degree alkyl halides to form alkanes containing a quaternary carbon atom. Reaction with acid chlorides. They react readily with acid chlorides to form ketones. For example, diethyl zinc acetyl chloride gives a product which on reduction of C2H5ZnCl gives butanone. Ketones are obtained in good yields because trialkyl zinc compounds react very slowly with them. Raffermatsky reaction. When an aldehyde or a ketone is added to the solution of an alpha haloester in presence of zinc, an organozinc compound is first formed, which then adds to the carbonyl group in a manner similar to the Grignard reagent to form a beta hydroxy ester. This reaction is called Raffermatsky reaction and is a useful method for preparing beta hydroxy esters, acids, and their derivatives. For example, ethyl bromoacetate on reaction with zinc in presence of dry ether gives organozinc compounds. Iodomethyl zinc iodide. Iodomethyl zinc iodide is an important organozinc compound and is obtained by the action of ZnCu couple on methylene iodide. It reacts with olefins to form cyclopropane derivatives. This reaction is called Simon-Smith reaction and is used for preparation of cyclopropane derivatives. The addition occurs in a stereospecific syn matter according to the following concerted mechanism. Organolithium compounds. Compounds in which lithium atom is directly bonded to a carbon atom are called organolithium compounds. Example: methyl lithium, ethyl lithium. Organolithium compounds are more reactive than Grignard reagents and also undergo a few additional useful reactions. Therefore, they are widely used in organic synthesis these days. Formation of alkyl lithiums. 1. By reaction of an alkyl halide with lithium. Alkyl lithium are generally prepared by treating an alkyl halide with lithium in hexene, benzene, or any other hydrocarbon solvent at a low temperature in an inert atmosphere of nitrogen or argon. Methyl bromide plus 2Li on reaction with N2 263 Kelvin in presence of dry hexene give methyl lithium plus LiBr. For the preparation of alkyl lithiums, hydrocarbon solvents are preferred over others since the use of ether not only increases Wood's reaction but also reacts with it. Diethyl ether plus N-butyl lithium gives butane, which after gives ethylene plus CH3CH2OLi. 2. By metal-metal exchange, alkyl lithiums can be readily prepared by the replacement of one metal by another. For example, dimethyl mercury plus 2Li gives ligroin at 338 Kelvin ethyl lithium plus Hg. Chemical reactions of alkyl lithiums. The Cli bond is more polar than Cmg bond. Therefore, alkyl lithiums are more reactive than Grignard reagents. Except a few differences, their chemical behavior is similar to that of Grignard reagents. Some of their important chemical reactions are discussed below. 1. Resemblance with Grignard reagents. They resemble Grignard reagents in most of their reactions. Some of these reactions are: number 1. Formation of hydrocarbon. Like Grignard reagents, they react with compounds containing active hydrogens to form the corresponding hydrocarbons. For example, CH3Li plus H2O gives methane plus LiOH. 2. Formation of primary, secondary, tertiary alcohols. A. Primary alcohols by action with formaldehyde. Formaldehyde plus alkyl lithium gives an additional product in presence of hexane on hydrolysis, which gives 1 degree alcohol plus LiOH. Like Grignard reagents, alkyl lithium compounds are also react with ethylene oxide to form primary alcohols containing 2 carbon atoms more than the starting alkyl and aryl halide. Phenyl lithium plus ethylene oxides give C6H5CH2CH2OLi, which on hydrolysis gives 2-phenyl ethanol. B. Secondary alcohols by reaction with aldehydes other than formaldehyde, acetaldehyde plus CH3Li in presence of hexane gives CH3 2-ice OLi, which on hydrolysis gives isopropyl alcohol plus LiOH. Tertiary alcohols by action with ketones. Acetone plus CH3Li on hexane gives CCH3 thrice OLi, which on hydrolysis gives tert-butyl alcohol plus LiOH. 3. Formation of ethers. By action with a monochloroether, CH3OCH2Cl, that is monochloromethyl ether plus CH3Li gives hexane, which gives ethyl methyl ether plus LiCl. Formation of aldehydes. By action with ethyl orthoformate or hydrogen cyanide plus CH3Li on reaction with hexanes gives CHCH3 and Li, which on hydrolysis gives acetaldehyde plus NH3 plus LiOH. 5. Formation of ketones. By action with any orthoester other than orthoforming ester alkyl cyanide. For example, ethyl orthoacetate on reaction with hexane gives CH3 CCH3OC2H5 twice, which on hydrolysis gives acetone plus 2 C2H5OH. Number 6. Formation of nitriles by action with cyanogen chloride. CH3Li plus cyanogen chloride on reaction with hexane gives acetonitrile plus LiCl. Reaction with alkyl halides. Alkyl lithium react with alkyl halides to form alkanes. For example, ethyl lithium plus CH3MgBr on hexane gives propane plus LiBr. Reaction with aryl halides. Aryl halides undergo nucleophilic substitution reaction by elimination, addition or benzene mechanism. For example, orthofluoroanisole gives benzene on reaction with C6H5Le, and after addition of C6H5Le it gives 3-phenylanisole. 8. Reaction with heterocyclic compounds. Heterocyclic compounds undergo nucleophilic substitution reaction by biomolecular displacement mechanism. For example, pyridine, which on nucleophilic aromatic substitution gives 2-phenylpyridine plus LiH. 2. Difference from Grignard reagents. Organolithium compounds, being more reactive than Grignard reagents, undergo some additional reactions as discussed below. 1. Action with carbon dioxide. Grignard reagents yield carboxylic acids with carbon dioxides, while organolithium compounds yield ketones. The difference is due to the reason that organolithium compounds are more strongly nucleophilic than Grignard reagents and thus react further with the intermediate resonance stabilized carboxylate anion giving ketones. 2. Action with carboxylic acids. Alkyl lithium compounds react with carboxylic acids yielding ketones as the main product. Grignard reagents, on the other hand, give alkanes corresponding to the alkyl group of the Grignard reagent. 3. Addition to carbon-carbon double bond. Unlike Grignard reagents, organolithium compounds add to simple alkenes to give a mixture of compounds. The addition occurs at high pressure. For example, RLi plus CH2 double bond CH2 gives RCH2CH2Li, which on reaction with CH2CH2 gives RCH2 4Li, etc. Formation of tertiary alcohols. Organolithium compounds, being more nucleophilic and smaller in size than the corresponding Grignard reagents, add to sterically hindered ketones to form sterically hindered tertiary alcohols. Grignard reagents, on the other hand, do not give such addition reactions. For example, isopropyl lithium adds to diisopropyl ketone to yield triisopropyl carbinol. In contrast, when isopropyl magnesium bromide is added to dipropyl ketone, the expected tertiary alcohol is not formed. Instead, reduction of the ketone by the Grignard reagents occurs to give diisopropyl carbinol and propylene. 5. Reaction with alpha-beta unsaturated carbonyl compounds. Organolithium compounds, being more nucleophilic, predominantly undergo 1,2 addition to alpha-beta unsaturated carbonyl compounds, whereas Grignard reagents give mainly 1,4 addition product. For example, benzyl acetate on reaction with CS3 MgBr gives 1,4 addition product, which on hydrolysis gives 4-phenyl pentane 2-on. Thanks for watching.